Section 5.2 is titled Logarithms and Exponential Models. So in this section, we're going to look at using exponential functions to model real-world scenarios, and then we'll use logarithms to either solve for some part of our model or to look at where two models are equal to each other or intersect. And then in section 5.3, we'll actually look at logarithmic models. So we'll look at both, but we're going to start with exponential models first in 5.2. So before we get to our first modeling type, which is doubling time, I want to do a quick review of our exponential functions. So we have two types of exponential functions that we've been using, our constant or standard one, which is y is equal to ab to the x, and then our one that is for continuous growth, and that's y is equal to ae to the kt. So I want to go through and make sure that we're clear on what each of these parts of the equation are. So for our first one, we're looking at what the initial amount is. And for both of these, the initial amount is represented by the same letter, and that's the letter A. Okay, so whatever number is in this place that's representing this letter A is going to be our initial or starting amount. Right, the next thing we're going to look at is our growth factor. So in our constant exponential growth, we represent our growth factor with the letter B. Okay, and if we think back to section 4.1, we know that B is equal to 1 plus R. So if for some reason we do need to calculate that, that's how we do that. And then our growth factor in the continuous one is going to be e to the k. Okay, so there's our two growth factors. The next thing we're going to look at is our growth or decay rate. So in our constant form, we represent that with the letter R. And if we need to find that, that's equal to b minus 1. And then in our continuous one, our growth or decay rate is the letter k. All right, and then let's look at when each of these functions is either growing or decreasing. So we do have to assume that a is greater than 0, so a is a positive number, our starting amount is positive. And if that's the case, then we know that our function is growing in the y is equal to ab to the x form if either r is greater than 0. So if we have the value of r, we know it's greater than 0, that'll tell us we're growing, or if we have the value of b and that's greater than 1. Okay, and then conversely, if we're looking for where it's decaying, that would be where r is less than 0. So we have a negative value for our growth rate. And what that does is it means that b is going to end up somewhere between 0 and 1. So if b is between 0 and 1, then we know that our function is decreasing or decaying. And then in terms of our continuous one, a is ae to the kt. It's growing if k is positive. So if k is greater than 0, our exponent is positive, and then it'll be decaying or decreasing if k is less than 0 or negative. All right, so there's kind of a quick review of both of our two exponential functions. And then I want to take a look at how do we convert back and forth between these two. So how do I get from a continuous one to a constant one and vice versa? So to do that, I can actually set these two equations equal to each other. I have ab to the x is equal to ae to the kx. Okay, so they both have an a, so I can cross those a's out. And that leaves me with b to the x is equal to e to the kx. So since they're both raised to a power of x, I can cancel that out as well. And I'm left with just b is equal to e to the k. So if I need to switch from one to the other, I'll either have b or I'll have the e to the k piece, and then I'll be able to solve back and forth. So one thing to be careful about when you're reading a word problem, the rate that they give you is either going to be r or k. And that's going to depend on the context. So if it says it's continuous, then they've given you the letter K. They're telling you something like it's per day, per hour, something like that, then they've generally given you R for the standard or constant growth. Okay, and then one thing to note, R and K will be fairly similar, but they are not exactly equal. So you can't just substitute one out for the other. All right, let's take a look at some example problems of identifying these pieces and then switching back and forth. All right, the first equation we're going to look at, we were given the constant or standard form, y is equal to 5 times 1.2 to the x. So we're going to identify our growth factor b and our growth or decay rate r. So you know b is whatever number is being raised to the x, so that's 1.2. And then to get to r, we just subtract 1 from b. So that leaves us with 0.2, or if you're interested in the decimal, that is about 20%. That is exactly 20% there. All right, now we need to convert this over to the continuous form. So instead of having 1.2, I need e to the k in here. So to do that, we'll use this b is equal to e to the k formula. We know our b is 1.2. So what that gives me is 1.2 is equal to e to the k. And if I apply the natural log to both sides, then that'll tell me what k is equal to. So k is roughly equal to, let's see what we get here, ln of 1.2. So you get about 18, a little over 18% there, which is close to our r of 20, but not exactly equal. So I have k is about 0.1823. So now I can fill that into my continuous one. So I get y is equal to, and remember they're going to have the same starting value. So I'll still have a 5, but now it'll be e to the 0.1823x. Right, so there is my equation. My growth factor is e to the 0.1823. And then my growth or decay rate, that's the k, my exponent, 0.1823 or 18.23%. All right, this next one, we were given kind of the opposite. So we have our continuous version, and then we're going to have to backtrack to the constant. So if y is equal to 6e to the negative 0.04x, so my growth factor is e to the negative 0.04, and k is my growth or decay rate, that's negative 0.04 or negative 4%. Okay, so we do have that that's decaying then. So it is a decay. This other one was a growth because it was positive. Okay. And then we need to convert this e to the negative 0.04 to b. So it's actually easier to go from the continuous to the constant. And that's because we don't have to solve anything. We just need to put a couple of buttons in the calculator. So I know b is equal to negative 0.04. And I'll just put that in the calculator. So we get e is equal to negative 0.04. So I get 0.9608 if we round, or 0.7, either way. And so that gives me b. So you can fill that in here, 0.9608. Okay, and that is what we would expect. We already noted that it was decaying, so I would expect that b is going to be a number between 0 and 1, which is what I have. And then to get r, I'll subtract 1 from that. So I get negative 0.0392. Or negative 3.92%. So again, close to the negative 4%, but not exact. And then the equation is going to be y is equal to ab to the x. So my a was 6, and I'll keep that, and then 0.9608 to the x. All right, down to our last one. We're going to go back the other way this time from our standard or constant to the continuous. So I have y is equal to 10 times 0.91 to the x. So since my b is between 0 and 1, I do know that this is decaying. Okay, and so that means I am going to expect that I'll get a negative k once we get over here in order for that to match. So my growth factor is 0.91. That's just the b. And if I subtract 1 from that, I get negative 0.09 or negative 9%. And then to get the continuous, I know that 0.91 is equal to e to the k. So I take the natural log of both sides. So remember that natural log and e are inverses, so that's why these get wiped out, and I'm left with just k. So let's see what we get. We're expecting something in the neighborhood of negative 9%. Let's see what we actually get here. 0.91. So k is about negative 0.0943 here, which is what we would expect. We expect negative from the decay, and it is reasonably close to r, so we feel pretty good about that. I'm going to go ahead and put this in here. So negative 9.43%. My growth factor is e to the negative 0.0943. And then if I put that all together for the equation, I have y is equal to, and I have the same starting amount of 10, and I have e to the negative 0.0943x.